In Part 1 of Lecture 3, we will discuss an introduction to processes. Before defining the term process, it's useful to summarize some of the concepts that we learned in Lectures 1 and 2. A computer platform consists of a collection of hardware resources, such as the processor, main memory, I/O modules, timers, disk drives, and so on. Computer applications are developed to perform some task. Typically, they accept input from the outside world, perform some processing, and generate output. It is inefficient for applications to be written directly for a given hardware platform. The principal reasons for this are as follows. Numerous applications can be developed for the same platform. Thus, it makes sense to develop common routines for accessing the computer's resources. The processor itself provides only limited support for multiprocessing. Software is needed to manage the sharing of the processor and other resources by multiple applications at the same time. When multiple applications are active at the same time, it is necessary to protect the data, I/O use, and other resource use of each application from the others. The operating system was developed to provide a convenient, feature-rich, secure, and consistent interface for applications to use. The operating system is a layer of software between the applications and the computer hardware that supports applications and utilities. We can think of the operating system as providing a uniform, abstract representation of resources that can be requested and accessed by applications. Resources include main memory, network interfaces, file systems, and so on. Once the operating system has created these resource abstractions for applications to use, it must also manage their use. For example, an operating system may permit resource sharing and resource protection. Now that we have the concepts of applications, system software, and resources, we are in a position to discuss how the operating system can, in an orderly fashion, manage the execution of applications so that resources are made available to multiple applications, the physical processor is switched among multiple applications so all will appear to be making progress, the processor and input-output devices can be used efficiently. The approach taken by all modern operating systems is to rely on a model in which the execution of an application corresponds to the existence of one or more processes. You may recall from Lecture 1 that we had several definitions of the term process, including a program in execution, an instance of a program running on a computer, the entity that can be assigned to and executed on a processor, and a unit of activity characterized by the execution of a sequence of instructions, a current state, and an associated set of system resources. We can also think of a process as an entity that consists of a number of elements. Two essential elements of a process are program code, which may be shared with other processes that are executing the same program, and a set of data associated with that code. Let us suppose that the processor begins to execute this program code, and we refer to this executing entity as a process. At any given point in time, while the program is executing, this process can be uniquely characterized by a number of elements, including the following: an identifier, a unique identifier associated with this process to distinguish it from all other processes; state, If the process is currently executing, it is in the running state. Priority. Priority level relative to other processes. Program counter. The address of the next instruction in the program to be executed. Memory pointers include pointers to the program code and data associated with this process, plus any memory blocks shared with other processes. Context data. These are data that are present in registers in the processor while the process is executing. Input-output status information, including outstanding I/O requests, I/O devices such as disk drives, assigned to this process, a list of files in use by the process, and so on. Accounting information may include the amount of processor time and clock time used, time limits, account numbers, and so on. The information in the preceding list is stored in a data structure, most commonly called a process control block, that is created and managed by the operating system. The significant point about the process control block is that it contains enough information so that it is able to interrupt a running process and later resume execution as if the interruption had not occurred. The process control block is the key tool that enables the operating system to support multiple processes and to provide for multiprocessing. When a process is interrupted, the current values of the program counter and the processor registers, or context data, are saved in the appropriate fields of the corresponding process control block, and the state of the process is changed to some other value, such as blocked or ready. These will describe somewhat later. The operating system is now free to put some other process in the running state. The program counter and context data for this process are loaded into the processor registers, and this process now begins to execute. Thus, we can say that a process consists of program code and associated data, plus a process control block. For single processor computers at any time, at most one process is executing, and that one process is in the running state. As we just discussed, for a program to be executed, a process or task is created for that program. From the processor's point of view, it executes instructions from its repertoire in some sequence dictated by the changing values in the program counter register. Over time, the program counter may refer to code in different programs that are part of different processes. From the point of view of an individual program, its execution involves a sequence of instructions within that program. We may characterize the behavior of an individual process by listing the sequence of instructions that execute for that process. Such a listing is referred to as a trace of the program. We can characterize behavior of the processor by showing how the traces of various processes are interleaved. Let's take a look at a very simple example. What you see on the slide shows a memory layout of 3 processes. To simplify the matter, we assume no use of virtual memory. Thus, all 3 processes are represented by programs that are fully loaded in main memory. In addition, there is a small dispatcher program that switches the processor from one process to another. The figure on the screen shows the trace of each of the processes during the early part of their execution. The first 12 instructions executed in processes A and C are shown. Process B executes 4 instructions, and we assume that the 4th instruction invokes an input-output operation for which the process must wait. Now, let's view these traces from the processor's point of view. This slide shows the interleaved traces resulting from the first 52 instruction cycles, and for convenience, these instruction cycles are numbered. In this figure, the shaded areas represent code executed by the dispatcher. The same sequence of instructions is executed by the dispatcher in each instance, because the same functionality of the dispatcher is being executed. We assume that the OS only allows a process to continue execution for a maximum of 6 instruction cycles, after which it is interrupted. This prevents any single process from monopolizing processor time. As the figure shows, the first 6 instructions of process A are executed, followed by a timeout and the execution of some code in the dispatcher, which executes 6 instructions before turning control to process B. After 4 instructions are executed, process B requests an input-output action for which it must wait. Therefore, the processor stops executing process B and moves on, via the dispatcher, to process C. After a timeout, the processor moves back to process A. When this process times out, process B is still waiting for the input-output operation to complete, so the dispatcher moves on to process C again.